Thank you so much for having me here. It's a pleasure to be here. So I'll explain this. So in fact, as I was preparing this talk, I decided that maybe I should take a more sort of broader view of the subject. So I changed the title. That might be bad form, but Problems in Local Galois Deformation Theory. And if you want, the original title is kind of a subtitle to that title. OK. So let's begin with, I'm going to start with some motivation. So the motivation for what I'm going to talk about is a landmark theorem, formerly the Taniyama-Shimura-Weil conjecture, now known as the modularity of elliptic curves. So this is then a theorem of Wiles, Taylor-Wiles, and finished off by Broy, Conrad, Diamond, Taylor. And it says that any elliptic curve over the rational numbers is modular. Now, there's sort of many ways of saying what it means for many equivalent ways of defining what that modular means. For the purposes of our talk, we're going to say elliptic curve is modular if it's the Galois representation, the p-adic Galois representation on the torsion points of the elliptic curve is isomorphic to a Galois representation coming from modular form. So this is so the theorem then is this relationship between elliptic curves, an arithmetic object, and the modular forms, an analytic object. And so one of the big techniques that was introduced in the proof of the modularity conjecture was now known as modularity lifting. All right. So if we take any p-adic representation rho, then we can consider the rho bar the reduction of that representation mod p. And so the idea of modularity lifting is that somehow we want to say that if rho bar comes from a modular form, then in fact rho comes from a modular form. And so the sort of prototype for this sort of theorem is modularity lifting theorem. It says that if rho is a p-adic representation of, say, the absolute Galois group of Q, and it satisfies some conditions, then rho bar modular implies rho is modular. So these x, y, and z are not meant to be like specific conditions, but rather, depending on whoever's proving the theorem will then sort of give the conditions x, y, and z. And in some cases, it may be more than 3 conditions. So this has a nice picture. So if we start with our residual representation rho bar, then we can consider the sort of moduli space, a deformation space of all p-adic representations which lift that rho bar. And of course, our representation rho is then one of them. And so maybe the sort of intuitive picture is that you have the guys which come from the representations which come from modular forms sitting inside the space. Let's see, can I do it? And we want to try to pin down what this modular locus is. The dimensions here don't necessarily line up with any actual dimensions of these things. Okay. And so how are we going to identify this? Sort of intuitively, might one identify this locus? Well, we want to sort of think about what sorts of conditions we can put on Galois representations. And so the most common conditions then are sort of local conditions. So a local condition now, so if we have a representation of the global Galois group, then for each prime L, we can look at the restriction of that representation to the local Galois group of L-adic for each prime L, and then we can impose some conditions on what that restriction should look like. So a very simple example of that is we can consider we can impose the condition that our representation be unramified at a prime L. And so what we're going to be talking about for the rest of the talk is that the most subtle of these conditions, which occur when we look at L equals P. So that means when we're studying p-adic representations of the Galois groups of p-adic fields. All right, so now we'll go ahead and fix notation. We take K to be a finite extension of QP, and gamma K will be the absolute Galois group. And now let's fix a residual representation, rho bar, of that local Galois group into, say, GLN of FP. All right? And so now there is a space which we'll call the universal local deformation space, which parameterizes deformations of this rho bar. So now we're purely in the local setting. So in the proof of the modularity of elliptic curves, an important local condition that one had to understand was the flat deformation space. So the flat deformation space, so it's a subspace of all deformations, and it consists of those representations that come from finite flat group schemes over the ring of integers of OK of k, the ring of integers of k. All right, so this is a very strong condition on a representation that it has this geometric structure that comes from a finite flat group scheme. And so, of course, the motivation then is the example, which is if we have an elliptic curve over k which has good reduction, then its associated the Gauss representations on its p to the n torsion points are flat for all n. And so in particular, our rho sub e would then lie in the flat locus. So this was an important again in the modularity of elliptic curves to understand what this to study this flat deformation space. But for more general modularity lifting results, one wants to study. There are many other deformation spaces that we're interested in, which contain representations coming from modular forms. So so here are two possible generalizations that one is interested in. So there's sort of what one might call the higher weight case. And so these are crystalline deformation spaces. And we're with so-called Hodge type mu. So in some sense, the flat deformation space corresponds to Hodge type 0, 1. And if you want sort of motivation for these crystalline deformation spaces, then if you have a modular form of weight k with with no level at p, then the representation would be crystalline with Hodge type 0 k minus 1. Also, I won't say too much about it, but that also you can look at higher level forms, which correspond to semi-stable deformation spaces, or more generally, potentially semi-stable deformation spaces. So, what sorts of questions in general could one ask about these objects? So there are many questions one can ask, but maybe two of the more important ones. The first one, and the one I'm going to focus on, is what are the connected components of the flat deformation space, or the crystalline deformation, or even the semi-stable one? And in this case, we really only care about what happens after we invert p, though. And so this comes out of some of the techniques that are used in modularity lifting that one is interested in this question. There's also, I shouldn't fail to mention that there's another interesting question, which is what is the structure mod p of these deformation spaces? And so this is related then to the Broglie-Mazard conjecture. All right, so what do we know, or some of what we know? So when k is unramified over qp, and our weight is relatively small compared to p, then we're in good shape. The crystalline deformation ring is smooth, and its generic fiber has just one component. Okay. But now, as soon as we introduce ramification in k, then things become much more complicated. And so in that situation, I believe that the only progress really is in the case of GL2, where a number of authors, beginning with the work of Kissen and then also M.A., G, and Hellman, they eventually combine those results together, and you're able to answer question 1 for the flat deformation ring, and importantly, with no restrictions on k. There is also some progress in the case of GL2 on the Broglie-Mazard conjecture. Okay. All right. So I want to say a word about sort of what goes into this second bit. How do we study this flat deformations when k is ramified? And so this is all those results are a consequence of this technique introduced by Kissen. So Kissen's technique, groundbreaking technique, was to introduce a resolution of it doesn't matter, it could be the flat, crystalline, semi-stable, but we can introduce a resolution of those deformation spaces, which is a moduli space of linear algebra data. And this uses deep results from integral p-adic Hodge theory. And so this resolution exists in general, but importantly, one can actually understand the structure of this resolution in the flat case. So in the flat case, one actually understands the singularities of this resolution and using local models of Shimura varieties. And so this was essential in answering that connected components question. In the flat case, one can think of this moduli space here as being, we have a flat deformation, so the moduli space is intuitively the fibers are a representation together with a finite flat model, a finite flat group scheme. All right, and so now I want to talk a little bit about my thesis, just briefly. And so what I worked on was a sort of generalization in a slightly different direction, which is G-valued Galois deformations. So now will G be a reductive group over ZP, or really any more finite extension, sort of finite extension of ZP, and let rho bar be then a residual representation valued in the finite points of that group over a finite field. One can similarly define a universal deformation space of G-valued Galois deformations, and there are corresponding analogs of the crystalline and semi-stable subspaces with fixed Hodge type mu. And so then theorem, so the theorem of my thesis is that there exists a projective morphism, so a resolution then of the, so if you want crystalline and more generally the semi-stable, which is an isomorphism with P inverted. And furthermore, and this is kind of maybe the harder point, which is that if that mu is sufficiently small, then we can actually understand the local structure of that resolution. So the local structure is equivalent to that of a local model. And so this is this sufficiently small is sort of the analog of flat in this case. Okay, and so one should maybe think of this theorem as being sort of a first step towards studying flat deformations. Studying sort of what you might call studying these crystalline deformation spaces with valued in G. Okay, and so now I want to sort of, I want to mention then a couple just sort of parting points. One is that one would like to understand the structure of this resolution in the higher weight situations. So when mu gets bigger, this seems to be a tricky and perhaps very difficult problem. But one certainly anticipates and hopes that any results on this connected connection would then lead to better modularity lifting theorems. Of course, there's plenty of work to be done on just the side of proving the modularity lifting theorems as well. So that's all I had to say, and thank you so much.
Thank you very much.